All right, let's talk about something truly mind-bending, quantum computing. We're about to dive into a technology that could completely change the game, from creating new medicines to figuring out the deepest secrets of the universe. So yeah, buckle up. This is going to be fun. I mean, just think about it for a second. The really big, hairy problems we face, designing drugs to cure diseases, creating materials we've never even dreamed of, maybe even getting climate change models that are spot on. A normal computer tackles these things step by step. But what if you had a computer that could look at every single possible solution, all at the same time? Well, that's the wild promise we're talking about today. So how in the world does a quantum computer pull off a feat like that? It's not just about being faster or smaller. Nope, the secret is it thinks about information in a completely different way, right from the most basic level you can imagine. Okay, so on the left, you've got the classical bit. This is what all of our current computers run on. It's super simple, like a light switch. It's either off, a 0, or it's on, a 1. That's it. But on the right, you have the qubit, and that's the heart of a quantum computer. It's not just a switch. It's more like a dimmer. It can be off, on, and kind of everything in between, all at once. Now, this ability to be in multiple states at the same time, it comes from the super strange but totally awesome world of quantum physics. We're going to call it the quantum weirdness. And trust me, it's the engine that makes this whole thing go. The first key idea here is something called superposition. It's this wild concept that a qubit can be both a 0 and a 1 at the exact same time. This is the secret sauce. It's what lets a quantum computer hold and work with a ridiculous number of possibilities all at once. And honestly, this is the best way to picture it. Think about flipping a coin. While it's spinning in the air, is it heads or tails? No, it's kind of both, right? A blur of potential. It's only when it lands, when we measure it, that it has to pick a side. That, right there, is the magic of superposition. And then there's entanglement, a phenomenon so bizarre that even Albert Einstein was freaked out by it, calling it spooky action at a distance. You can link two qubits together so their fates are intertwined. If you measure one and see it's a 0, you know instantly that its partner is a 1. It doesn't matter if it's right next to it or on the other side of the galaxy. So what's the point of this? It's all about teamwork on a cosmic scale. This deep connection creates a perfectly in-sync team of qubits that can work together to solve problems in ways a classical computer just can't. It's not about sending messages, it's about this powerful shared information. Okay, so we've got these incredible, almost magical properties, superposition and entanglement. But how do you actually use all this weirdness to calculate something? How do we turn these mind-bending ideas into a real problem-solving machine? Let's get into it. We control these qubits using something called quantum gates. You can think of them like the familiar and, or, and not gates in your computer, but on a whole other level. These gates are the precise instructions we use to manipulate a qubit's state, to tweak its probability, to rotate it, or to entangle it with another one. A quantum calculation pretty much boils down to a 3-step process. First, you get your qubits all set up in a specific starting state. Then, you run them through a carefully designed series of these quantum gates, which makes them interact and evolve in really complex ways. And finally, you measure the result. This collapses them out of that quantum state into a single classical answer, hopefully the solution you were looking for. By setting up this whole dance just right, you basically create a wave of possibilities, where all the wrong answers cancel each other out and the right answers get stronger. This is where that incredible quantum speed-up comes from. The power to solve certain types of problems way, way faster than any classical computer ever could. I know, this all sounds like something straight out of science fiction, doesn't it? A machine from the future? But what's the reality? Where are we today on this journey to building a full-on, error-free quantum computer? Well, the honest answer is we're still at the very beginning. Right now, we're living in what experts call the NISQ era. That stands for Noisy Intermediate Scale Quantum. And it basically means that the quantum computers we have today, from the big labs at Google and IBM to cool new startups, are still kind of small and really, really sensitive to making errors. But don't let that fool you. The progress we're seeing is moving at a breakneck speed. The challenges are no joke. We're fighting against high error rates and something called decoherence, which is just a fancy word for when a qubit loses its quantum magic. It's like a delicate soap bubble just popping because of a tiny vibration or a little bit of heat. And the hardware, it's incredibly fragile, often needing to be kept colder than deep space just to work at all. But even with all those hurdles, we're already starting to see the potential.
We're right on the edge of using these early quantum machines to do incredible things, like simulating molecules to invent new drugs, making global supply chains way more efficient, designing brand new materials from the atom up, and maybe even building smarter AI.
So let's bring it all home. What does this really mean for us? Why should you and I care about this strange, super fragile, and unbelievably complex technology? Let's talk about the big picture. And this is maybe the most important thing to remember. A quantum computer isn't going to replace your laptop or your phone. That's not the goal. Think of it more like a specialized scientific instrument designed to solve a very specific class of problems. The impossible problems, the ones that are just completely out of reach for even the biggest supercomputers we have today. And that leaves us with a pretty awe-inspiring thought. We are building a tool that could fundamentally change our world. It's like a key that could unlock secrets of the universe we never thought we'd know. The only question is, what are we going to build when the word impossible doesn't mean what it used to?